Remember the good old days when your robot was young and romantic? Remember how his heart beat with fire? That special electrochemistry that gave him the power to perform your every dream? Well, dreams fade. A careless adventure or two, and before you know it, unsightly rust. Why does rust develop so quickly? Fortunately, we've been studying all those little services your robot will need. And we've explored the principles of electrochemistry within the heart of the robot, the battery. Fortunate because those same principles will help us to understand rust, which is nothing more than tiny electrochemical cells forming over the skin of our Iron Man. Let's consider a single salty tear of happiness falling on the head of our romantic robot. We'll look at the droplet in cross-section as it rests on the iron. The drop is surrounded by air. Air contains oxygen. Because of the drop, the concentration of oxygen next to the iron surface will be low in the center of the drop and higher at the edge of the drop. The edge behaves like a half cell, at which reduction occurs. Here, oxygen combines with water and electrons to form hydroxyl ions. But where do the electrons come from? The center of the drop acts as the other half cell, at which oxidation occurs. The iron in the center of the drop acts as an anode. Here, iron atoms become oxidized as they lose electrons to become ferrous ions in the salt solution. The electrons flow through the iron to the edges of the drop, where they are required in the reduction reaction. This matches the electron flow through the wire of an electrochemical cell. Now remember that an electrochemical cell requires the salt bridge. Without it, the cell very quickly becomes polarized and the flow of charge stops. The movement of the ions in the salt bridge prevents polarization from occurring and enables the cell to keep operating. The droplet of salt solution on the iron acts as the salt bridge. The negative ions, or anions, move from the edge of the drop to the center. This would include the hydroxyl ions and the chloride ions. The positive ions, or cations, move from the center of the drop to the edge. This involves the migration of ferrous ions and sodium ions. When ferrous ions moving in one direction encounter hydroxyl ions moving in the other, an insoluble solid, ferrous hydroxide, is produced. This substance is immediately oxidized to produce a hydrate of ferric oxide, the material commonly known as rust. This rust concentrates between the half cells, which are formed between the center and the very edge of the drop. From above, we can see that the rust concentrates in a ring between the center and the edge of the drop. So we can see that each droplet of salt solution that falls on the robot produces a tiny electrochemical cell. We can write half-cell reactions for rusting, just as we did earlier for electrochemical cells. At the anode, iron is oxidized to form ferrous ions. At the cathode, oxygen is reduced in the formation of hydroxyl ions. The two half-cell reactions add together to describe the overall reaction. You may wonder why ordinary raindrops also cause rusting. Well, raindrops contain dissolved materials, such as carbon dioxide and sulfur dioxide. These substances readily react with water to form ions. The result is very much like that of salt water. So, just what can we do to protect our iron treasure from embarrassing skin conditions or worse? We have time to consider several possibilities. We could make our robots of metals, such as gold or platinum, which are not readily oxidized. But can we afford it? Another possibility is to galvanize an everyday iron robot. Galvanizing means a bath in molten zinc. Zinc protects the iron for a simple reason. A look at the reduction table shows why. Since we are considering oxidation reactions, reverse the equations and reverse the signs on the potentials. Then we can compare oxidation potentials. Zinc's potential to oxidize is higher than that of iron. And that's what happens. Oxygen reacts with the zinc to form zinc oxide. Even if the zinc is scratched and the iron is exposed, the zinc on either side of the scratch is more likely to be oxidized, protecting the iron. As the zinc atoms combine with oxygen to form zinc oxide, they form a layer which protects both the zinc and the iron. Unfortunately, that turns yesterday's shiny, bright star into today's gray servant, protected but dull. Another version of this kind of protection is a little more flashy. Robot jewelry. Let's rivet on a bracelet of magnesium. Now, look at the reduction potentials of iron and magnesium. Reverse their reduction potentials, and we see that magnesium has the higher oxidation potential. When a drop of salt water lands on the robot, magnesium becomes the anode where oxidation occurs. The electrons released from the magnesium travel to the iron cathode, where they are passed into the drop. Since the iron is turned into a cathode, this is called cathodic protection. And the magnesium is called a sacrificial anode, since it reacts and erodes away. So, in the end, electrochemistry can be both a nuisance and a useful tool for keeping a romantic robot in at least serviceable condition. Now, the best is yet to come. In the next program, we will explore how the normal electrochemical reactions of a battery can be reversed to create a robot that's really flashy.